This is the lesson for Tuesday, March the 16th, over section 7.1, Graphing Exponential Functions. So if you take a look at the handout that you'll receive, you're going to see at the top in the box that it talks about exponential functions, and there's some basic information you need to know about exponential functions. First off, an exponential growth function looks like this. You can see the x and y axis, and it is a graph that rises from left to right, and the x-axis serves as a horizontal asymptote, which is the line y equals 0. One thing you need to know about an exponential graph is that the base tells you whether it's exponential growth or exponential decay. And in the case where the base is a number greater than 1, it will look like an exponential growth graph. With exponential growth graphs, the domain is all reals. You can see that there. And the range is y greater than 0. And as I said, the horizontal asymptote is y equals 0. And on the left end of the graph, as x approaches negative infinity, y will approach 0 because it gets as close to 0, as close to the x-axis as possible without crossing it. An example of this type of function would be y equals 2 to the x. And we can make tables of values to help us graph them. We'll see that below in a moment. Exponential decay graphs look like you see there to the right. They fall from left to right. And what distinguishes a decay graph from a growth graph is the value of the base. It is a number between 0 and 1, a fraction or decimal. An example, y equals the fraction 2/3 raised to the x. And the domain is all reals, the range y greater than 0, and the horizontal asymptote is the x-axis, or the line y equals 0, and as x approaches positive infinity, y approaches 0. It does this on the right end. Again, it gets as close to 0 as possible without crossing the x-axis. Then we have transformations of exponential functions. That's where graphs of exponential functions either shift vertically or horizontally, up or down. In the equation, h is a shift horizontally, k is a shift vertically, and a, the number out front, times the base, is going to give you a stretching or shrinking or a reflection of the graph either over the x-axis or the asymptote line y equals k. So let's look at some examples here. You can see below problem 1, we are graphing y equals 2 to the x. What we want to do is make a table of values like you see here. And good values to test are close to the origin. I test, of course, 0, positive 1, negative 1, and 2. And all I do is plug them in for my x, which is the exponent. And 2 to the 0 is 1. 2 to the first is 2. 2 to the negative first is 1 over 2 to the first, or 1/2. And 2 to the second is 4. And I plot those points. And if you take a look closely, you're going to see I graphed a point here, and here, and here, and 2 to the 4th. And that's what I drew through to get my graph. The domain, all reals, the range, y greater than 0. I knew before I graphed it was an exponential growth graph because the base was 2, and that is bigger than 1. And a is 1. That's just implied, and the horizontal asymptote is y equals 0. What happens when you change that equation to y equals the opposite of 2 to the x? Well, that's really meaning y equals -1 times +2 raised to the x. So the base is still +2, which implies an exponential growth graph, but because a is negative, we get what is called a reflection of the growth graph, which it reflects the graph over the x-axis. The horizontal asymptote is still y equals 0, and the domain is all reals, but y, the range, is less than 0. And you just plug in, and it gives you the opposite of the values you had in number 1, and you can see the reflection. If I graph number 2 on the same coordinate plane as 1, you get the graph in green. So you see that reflection. How about 3? In 3, we have a number out front. We have y equals 2 times 3 raised to the x. Again, a is 2, b is 3, so it is an exponential growth graph. We make our table of values, we graph our points. It looks very similar to number 1. Notice the domain and range are the same. And then in 4, when you put that -2 out in front times 3 to the x, we get the opposite of the values in 3. We plot them, and they are a reflection of that graph in number 3 over the x-axis. The only difference is our range is y is less than 0. So these are all growth or reflection of growth graphs because the base was a number bigger than 1. If you flip the sheet over, though, in the next two examples, the base is a number, in this case a fraction, that is between 0 and 1. In number 5, the base is 2/3. In 6, it is 1/3. In 5, a is 3, so it's going to stretch it. And we can again make our table of values, putting in 0, 1, -1, and 2. And we just let our calculator help us find values. They could be decimals to approximate. And it's an exponential decay graph because that base is between 0 and 1. So we know what it's going to look like before we actually graph. The horizontal asymptote, still y equals 0. Domain, all reals. Range, y greater than 0. And then finally in 6, a is -2, and the base is 1/3. So we have a decay graph, but because a is negative, it's a reflection of a decay graph. Horizontal asymptote, still y equals 0. I make my table of values, plug in and simplify, plot my points, and we get that reflection of a decay graph. So the domain's all reals, but the range is y less than 0. So this is the basics of graphing exponential graphs, making a table of values, sticking with the input values that are close to the origin, probably testing at least one on either side of 0 and testing 0, and getting enough points, and then knowing the basic shape so you can actually draw through the points that you've graphed. So what you're going to do is complete the worksheet that can be found in Canvas, but the substitute will also give to you. And for each problem, you're going to make a table of values. And so you can do this in the margin if you want. You can, do it on a separate sheet of paper, but you're just going to plug in. For instance, if I plug in -1 for the power, 2 to the negative first is 1/2, times 3 would be 3/2. If I plug in 0, 2 to the 0 is 1, times 3 is 3. If I plug in 1, 2 to the first is 2, times 3 is 6. And if I plug in 2, 2 to the second is 4, times 3 is 12. Obviously, I'm not going to graph all those points, but -1, 1.5 would be right there. 0, 3, right there, 1, 6, right there. And we have to have a little imagination when we draw our graph. It is an exponential growth. Oops, I didn't want that. It is an exponential growth graph. So it gets closer and closer to the x-axis, but theoretically does not cross the x-axis. I'm probably slightly off here, but the x-axis here is an asymptote that the graph approaches but doesn't cross. And you do want to draw that in. And that can shift if the graph is shifted up or down. That will shift the asymptote as well. Couple things to notice here are when you have some shifting. In number 5, this is a shift down 2 units, so that will affect the asymptote. It will be 2 units below, and that asymptote would be y equals -2. So keep that in mind when you draw in your graph and your asymptote. In number 6, the +5 here is actually a shift to the left 5 units. So when you make your table of values, you might want to start with like -6, -5, -4, -3, because when you plug in, -6 + 5 is -1, 2 to the -1st is 1/2. When you plug in -5, -5 + 5 is 0, 2 to the 0 is 1. When you plug in -4, -4 + 5 is 1, 2 to the 1st is 2. You kind of get the idea. -3 + 5 is 2, 2 squared is 4, and then you would graph these points and draw in your graph. And it's simply shifting your graph to the left. You'll see if you have -6, 1/2. Oops, you get the idea. -5, 1, -4, 2, -3, 4. So this is our graph, which is shifted left. It means the, oops, all right, the horizontal asymptote is still the same. And I think they ask you to state the domain and range here as well, so don't forget to do D and R. And you're going to see a theme. One side is exponential, and then the other side is decay. Or one side is growth, exponential growth. That's what I meant. And the other side is decay. And you go about it the same way. But that is your homework, completing that worksheet. And we will see you on Thursday. Have a great day.